Okay, in this short video we're going to demonstrate how to do a little bit of inspection on waveform. In this case we're going to use the WS2812 as found in this lovely hula hoop system. You probably remember this from before. You should see blue specks every now and then. But what we're going to do is we're going to connect this up to an oscilloscope to make sure that we're able to capture the waveform. So step one is getting it connected. Here we have 3 pins. We have our ground, our power, and our signal in the middle. So we're going to go ahead and we're going to connect our ground to our ground and our signal to its signal location here. Okay, now we're set up to make our measurements. Next thing we want to do is we want to make sure that our oscilloscope is set up properly. Currently we're on auto trigger, which means it's just going to continuously cycle, and I'll show you what that does in a second. We're set to about 2 volts peak to peak. This 2 volts peak to peak should be about right. It means that our waveform should be about this tall, since we're expecting a 5-volt waveform. And our time scale is set to about 4 microseconds. This should make sense in that each waveform should be about 2 bits or so per division across the screen. In order to grab just the first event, we're going to go ahead and set it to single trigger. Notice it's waiting for our trigger itself. And we're going to go ahead and cycle on the power once, and we went ahead and we've grabbed the signal. Now we don't have to leave this thing on because it went ahead and stopped because we did a single trigger. And so we've actually captured a single waveform in this screen. Okay, here's our single waveform from before. And this was again captured via just the single. Now what if I was to actually set this for a standard auto trigger? Well, in this case, if I turn it on, you'll find that the data isn't very useful. And I could try to catch it with a single catch, but being able to catch that first byte at the proper timing is probably not going to be reasonable. So instead, that's why we've set it up for the single trigger, and we've noted that the trigger is going to trigger at this level here, and it's only going to grab it once if we grab a single, because it's waiting at the startup. Okay, this allows us to catch that first 24 bits of the signal. So if we look at this specifically, we can see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 bits that look one way, and then we have 1, 2, 3, 4, 5, 6, 7, 8 bits that look another way. That's our 24 bits of this original signal. So we can actually see the information coming in and out of this that allows us to see what color it's done. And as you'll notice, we have our RGB, B being the B values, and we'll notice that in fact that is what the pattern of this LED hoop is doing. It's only doing the blue light. Okay. So one of the next things I want to look at is I want to look at our rise and fall times of an individual bit. One of the nice things about a digital storage oscilloscope is our ability to zoom in. So if we zoom in, we can see some interesting information. So for example, I'm going to scroll so that I can see the transition between the G bits and the B bits. So this right here, this slight small high followed by this low, this is a 0 in our system versus a 1 in our system. And in fact, we can double check our measurements of that by bringing up our cursors. Your cursors are set here, and they allow you to adjust them. You can see them here on the large scales we're zoomed out, so we'll go ahead and we'll zoom on in to something here. And then the other cursor is adjusted to B. That's what these little circles, these red circles with the different letters are, as they correspond to these multi-purpose knobs. So if we look at the width of this pulse, we get approximately a width of 304 nanoseconds. And we compare that to the data sheet. If we then look at the width of this lower pulse, we get a width of approximately 948 nanoseconds. So that would be for a 0 or a low. On the other end, if we look at a high, we see that we get an approximate on time of 616 nanoseconds and an approximate off time of 632 nanoseconds. And again, we can compare these to the data in the data sheet. However, to get access to rise and fall time, we can't just keep zooming in. We're beginning to see that we could to some degree, but notice how the line's getting fainter and fainter. It's because of how many samples the system has. In fact, this is the maximum distance that we can zoom in. If we attempt to use our cursors here, on this to try to get our 10 and 90% to get a rise time and a fall time, we'll find that we only have a certain precision, about 6.4 nanoseconds. So what we're going to do instead is we're going to take a full another sample, but we're going to try to only sample a single input. So this is zooming out in scale to try to get a very close view so we can get a full waveform and a half. We're going to set our position for our h-axis, our horizontal axis, not our h-axis, our time scale. Whoa, way off here in the space. Let's see if we can reset this. There we go. Set it back to the beginning so we don't have to keep scrolling all over the place. I'm going to scroll over just a little bit so I can try to grab two waveforms, assuming this. Then I'm going to go ahead and I'm going to turn off the system so that it's not doing the lights again. I'm going to set myself up to take a single measurement, like so. I'm going to capture that single measurement so I have good fresh data. I can turn the lights off so I don't waste power anymore. And now I should be able to zoom in. So to zoom in here, I can get very detailed. And I can get right on this edge if I wanted to. In fact, I can get so far on this edge that it's not really usable. There we go. There's about a percentage. So there we can actually see the rising edge. And you'll notice that we come from our 0 volts. We have that actually a little bit of a peak. This is true on all systems with a sharp edge because of the way the system rings is what it's called. And then you'll see it flattens out. Then using our cursors on this view, we're actually able to get our more precise measurement of our 10 and 90%, roughly in that realm. It's jumping around because it's actually, we're going sample by sample now at this rate because this oscilloscope only has that ability. And there we get a more precise rise time. Notice about 4.8 nanoseconds, which was significantly different than the rise time that we had from that wider sample point. Okay, and yeah, obviously there's a little bit of a tweak here in that as we adjust things, we can very easily get the same one as we had from before, just by picking different data points. So there's definitely a little bit of ambiguity at some point doing the 90 and the 10%. Let's go ahead and let's compare it though, looking actually using the measurement function. So if I bring up measurement, and I want to add a measurement to channel 1, and I want to do a different type of measurement, oops, excuse me, different type of measurement, I'm going to go ahead and I'm going to select rise time. Rising, where are we? Overshoot, amplitude, peak to peak. We don't want to count the number. There we are, just simple rise time. Add the measurement. All right. And while we're at it, since I'm going to want to see fall time, I'm going to go ahead and add this measurement as well. Okay, we can turn the menu off so we can see it. And we can see that the calculated rise time is about 5.99 nanoseconds. And if we zoom to here, we can see the calculated fall time about 4.32 nanoseconds. Zoom to our next waveform. Very similar rise time, and then very similar fall time. So this is a way we can actually zoom in and look at those pieces of information if we're so inclined to.